Okay, and when we talk about parent geometries, those are basic type geometries that define all the other geometries. Quiz 19. So when we talk about parent geometries, we talk about linear, trigonoplanar, tetrahedral, trigonobipyramid, octahedral, and there is one that is not in the Ebbing text, but it exists, pentagonal bipyramid. These are assigned, empirical formulas out of the VSEPR. If they are linear, you would recognize an AX2. AX3 for trigonoplanar, tetrahedral would be AX4, AX5 would be your trigonobipyramids, octahedral, AX6 and AX7. And so it seems kind of odd that we have 5, 6, and 7 attachments to the central element. That certainly violates the octet rule, but it does fit the geometry theory. At any rate, out of the tetrahedral, we can get an AX3E geometry, which is pyramidal. That is the exception that comes out of that. So the one that is not pyramidal B choice in that. So, any questions? Okay, so in the Vesper theory in AX6, as we saw just a moment ago, is the octahedral geometry. And we can draw an octahedron with a lazy square, put a couple big X in the middle, and then run a line up and down, and that is your octahedron. My artistic ability lacks a lot to be desired, but I hope that kind of gets the idea. I wouldn't, that's awful. Anyway, octahedral, and that is B choice, and that idea. Okay, which of the following is characteristic of hybrid orbitals? Well, all of these are very important. That's why I listed them all in there. So, character of hybrid orbitals. Well, the main thing for hybrid orbitals is that they have all the same energy. And if you don't remember me doing this, take carbon for example, has a helium core. Well, in the second energy level, it has an s orbital, and the p orbitals are at a higher energy level. And in the ground state, carbon looks like this. That's px, py, and pz. Well, the reasoning in here in forming hybrid orbitals is that these are not, you can't bond in this configuration. So what happens is the theory that develops this blends all of these together into hybrid orbitals. It takes the s and two p's if it's a trigonoplanar, the s and the p if it's linear, and s and all three of them if it's tetrahedral. So the hybrids can be linear, trigonoplanar, or if all of them are used, tetrahedral. So I'm just going to make the tetrahedral out of this, and we'll look at it in the second energy level. 1, 2, 3, 4. sp3, it takes one s, three p's, sp3, An electron is assumed to be promoted out in sp3, sp3, and each one of them is paramagnetic. If you don't remember that, I'll write the word. Paramagnetic is a single electron, non-bonded, and diamagnetic this is paired electrons. So all of these would be listed as paramagnetic, and so something's a bond in each one of these. Well, one of the things is that these are all the same energy. I'll move this up. Okay. One of the characteristics is when this hybridization takes place, it's like dropping apples and oranges in a blender, I suppose, and out comes same energy. They all have the same shape, and that is a distorted figure 8. So there's your hybrid orbital to visualize. If you have several, like in this case we have 4, they connect at the apex, and of course the apex is right there, and they form the geometries that minimize repulsion forces. So if this is an electron cloud, which is what it is, it all has negative charge, and if we were working with 4, we would see a tetrahedron in this form, and a lobe here, one there, and of course there would be one out here, and then bonding would take place here. Now, if a bond forms, a hybrid is no longer called an sp3. You recall, when the bond has a line of symmetry through both nuclei that are undergoing the bonding, then it's a sigma bond. So this is sigma, 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 and if this one up here, say, was just an electron pair, it would retain its identity as an sp3, but it would contain be diamagnetic. That is, it has paired electrons, non-bonded pair. I'll just write non-bonded pair. So I thought it'd be useful to kind of review a little bit more of this. It doesn't hurt to keep that in the back of your mind. In determining how many hybrids you need, you always determine the Vesper empirical formula, and however many electron pairs that you come out with based on that geometry, Vesper geometry, that's how many hybrids you have to have. Well, this one, all of the listing points were very important, and you remember about hybrid orbits. Determine some geometries. Here is PCl3, and it's asking 2 questions here. One is, what are the hybrids associated with the parent structure, and after you draw the structure, what is its geometry that's derived from here? Well, we have to determine the non-bonded pair. Well, from the structure we have 3 bonded pairs. That's the easiest part. Now the non-bonded pair is the valence number minus substrate over 2. Well, the valence is phosphorus plus 3 chlorides, which is equal to 5, plus 3 times 7, 26 here. And the substrate, it just deals with the 3 chlorides on the end, is 3 chlorides, and the substrate is always full at 8. Or if it's hydrogen, and only hydrogen, it does this, is 2. So everything's 8 except hydrogen, and it's 2. So 24. So we can apply these the valence number minus the substrate number, 26 minus 24 over 2, that gives me 2 over 2, or one non-bonded pair. So one non-bonded, 3 bonded pairs give me 4 electron pairs. 4 electron pair is an AX4 tetrahedral parent. And tetrahedral parent is always associated with an sp3 hybrid, where we take 4 and make the shapes here, here, and here. So there's your parent in stick form, I guess you'd say. And if we only have 3 attachments and 1 non-bonded pair, we put that non-bonded pair here. And so that would retain an sp3 identity, but it is diamagnetic with the lone pairs. These are becoming sigma bonds, which sp3 and actually it's an p orbital overlap here. But anyway, 1, 2, 3. The rule is the geometry is defined in terms of what's attached to the central element. Here, 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 and here. So this is pyramidal. So the parent is sp3 and the geometry is ax3e, and that is pyramidal. B choice, okay. Yeah, I can make a B. Okay. This is a good little example of what you'll have to deal with on exam day. I will provide several geometry problems and questions, so this would be a good one to copy down if you haven't already done so. Finally, here. How many hybrid orbitals are associated with ICl4 minus? Well, the number of hybrids equals the parent structure. That's basically so the parent structure is 4 bonded pairs and so many non-bonded pairs. Well, that would be valence minus substrate over 2. Well, we have 1, 4, 5 halogens. Each halogen is 7. So 7 to 4 is 28, but we've got a 4, 5, 7, 35. Sorry. But we have a minus charge on the ion, so you have to add 1 more electron. So 7 to 5 is 35 plus 1, 36 is our valence number. Everybody kind of catch that all right? Okay, okay. Substrate, you don't add or subtract valence. Is 4 to 8 is 32, and so divided by 2, and that's 4 over 2, or 2 non-bonded pairs. So we have 4 bonded pair and 2 non-bonded pair, or 6 electron pair, which gives you an AX6 parent in this structure. How many hybrid orbitals are associated? So we have 6 hybrids. And the outcome of this would be square planar. All right. I drew the AX6 parent. There is the AX6 parent right there. And we have 1, 2, 3, before in the plane, and if you recall, when we put in the 3 pairs, they go above and below the plane, and so this would be a square planer. And just to, let me see, that's C choice, get that out of the way. Just to review this now, if you have something of the nature, here is a structure, and what we want to do is find out how many pairs are associated with it. Well, I can tell you, and you can figure this also, is 4 bonded pairs and 1 non-bonded pair. You can check me on the math. Well, 4 and 1 is 5, so this gives an AX5 parent, but it gives an AX4E geometry. Okay, so drawing this out, this would be a trigonal bipyramid. Like that, and so we draw our lazy triangle, if you will, like that, and then pointer comes straight out of the top, and line comes straight out of the bottom, and we attach to the central element here. And so there is your AX4E, well, AX5 parent, the trigonal bipyramid. But the electrons, when you're working with a trigonal bipyramid, instead of entering above and below the plane, you recall we put the first ones into the plane and then attach everything around the central element right here, which was in this case sulfur, and then you have your fluorides in the here, and this becomes a seesaw. That's the AX4E geometry. And for hybrids of the AX5 geometry, it's an sp3d1. So you have 5 sp3d1s like that. And so you would have lobes that would show up like this, and one, of course, down here like that. With one of them would be an sp3d1 diamagnetic, because this would be a lone pair at the top. So you have sigma, 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 one and 2 sigmas, one up here and then one down below, and then this is an sp3d1 that's carrying a non-bonded pair. Like a lot to be desired, my artistic skill, but I think hope you get the idea of what I'm trying to get across to you on that.